Okay, we're back. My pen went out, so now I've got it charged. So like I was saying, when you have a table and you're trying to approximate g prime of 6, you could either use 4 comma 8 and 6 comma 12 and find the slope of that tangent, or the slope of that secant line, or you could use 6 comma 12 and 7 comma 13, or you could use 4 comma 8 and 7 comma 13. Okay, so when the value 6 is in your table, you have 3 choices. And so what I did, I put using 612 and 4/8, g prime of 6 is approximately equal to, and I just took 12 minus 8 over 6 minus 4, 4 over 2, 2. So basically, since this is our point, and I'm going to do this in a different color, this is the point. If we calculated the tangent line here, you can clearly see that it's not going to be parallel to the secant line. So our secant line was 1. So since g prime of 6 is approximately equal to 2, which is not 1, then the answer is no. And our justification was this. Okay, everything that we wrote is our justification. Part C, does Rolle's theorem apply on the interval 4, 9? Explain why or why not. And so what we would be looking for is not F, it would be G, sorry. So is G of 4, excuse me, equal to G of 9? And so our G of 4 is 8. And does it equal G of 9, which is 11? And it's like, no, it does not. 8 does not equal 11. Okay? So I'm going to just take this out of here. But since 8 does not equal 11, so f of 9 minus f of 4 divided by 9 minus 4 does not equal 0, right? Because you would have not gotten 0 there, and that's what you would have to have for Rolle's theorem. And then we go to D. Is there another interval where Rolle's theorem applies and justify? So I would be looking for points where the y values are the same, and I see the y value of 8 at x equals 4 and x equals 11 and x equals 15. So if you were doing from 4 to 11 on that closed interval, or from 4 to 15, or from 11 to 15, any of those closed intervals could work. So I'm going to say yes, Rolle's theorem could be applied on the interval for 11 or 11:15 or 4:15. In each of these intervals, the slope of the secant line is 0. And we already knew that, we had sketched a continuous and differentiable function, which were the other two things that would have to apply for Rolle's theorem to be able to be used there. But we did do that whenever we connected all those points. We created that continuous differentiable function. All right, so that moves us to example number 2. Let f be the function given by f of x equals x squared plus 2x minus 3. Find the number c that satisfies the conclusion of Rolle's theorem for f on negative 3, 1. So the first thing I'm going to check and make sure is that f of negative 3 is equal to f of 1, because that is what needs to be for Rolle's theorem to apply. So if I'm calculating that, I'm putting in negative 3 in my function, getting 9 minus 6 minus 3, which is 9 minus 9, which is 0. I'm also going to calculate f of 1 would be 1 squared plus 2 times 1 minus 3, 1 plus 2 minus 3, 3 minus 3, which is also 0. Okay, so the first part, we are making sure that just we can apply Rolle's theorem. So based on those things that we talked about, number 1, it is, f is a polynomial function, it is a parabola, it is continuous and differentiable. So we're going to say first that f of x is continuous on negative 3, 1, because it is a polynomial function. And number 2, f of x is differentiable on negative 3, 1. Also, f of negative 3 equals f of 1 equals 0. So Rolle's theorem applies. So now what I have left to do is I need to calculate f prime of x. So it will be 2x plus 2. And then go ahead and, if it were f prime of c, it'd be 2c plus 2. And then lastly, set my f prime of c equal to my slope of my secant line, which would be my f of 1 minus f of negative 3 divided by 1 minus a minus 3. But you know that that numerator is going to give you 0, and so I went ahead and just set it equal to 0, because I knew that that value was going to be 0. And this is telling me that this happens at c equals negative 1. So what happens at c equals negative 1? Well, this is an upward-facing parabola, and we said that for Rolle's theorem, it actually finds your maxes and mins. So this must be where your vertex is located. So not only did we find the c such that it's equal to the slope of the secant line, since the slope of our secant line was 0, we've actually found a minimum here because it's an upward-facing parabola, because it has a positive lead coefficient. We know that this would be our minimum. So we know that this is the x value of the vertex. If we wanted to put negative 1 back into the original function, we could find the y value of our vertex. It looks like if I put negative 1 in, I would get 1 minus 2 minus 3, which would be 1 minus 5, which would be negative 4. So just by, figuring out what that function's value is at -1 gave me the y value of my vertex. So that's what Rolle's theorem does for us. Okay, if we're able to use Rolle's theorem, if we have our f of a equal to our f of b, then it doesn't matter. They don't have to be 0. They just have to be the same number. So these both could have equaled 1. They both could have equaled 2. They both could have equaled 5. But when we would take our f of 1 minus our f of -3 over 1 minus a -3, this would, if they are the same number, it will always give us 0 here in the numerator. So that is the most important thing. Even though they actually equaled 0 for this example, they don't have to equal 0. They have to equal the same value, so that when you calculate your f of b minus f of a over b minus a, you get 0 over, any number. Here you're going to get 0 over 4. But 0 divided by any number, of course, except 0, is going to be 0. Okay? All right, example number 3. A sports car speedometer registers 50 miles per hour as it passes a patrol